It's not very uncommon in some physics and engineering contexts to have formulas that involve big messes of quotients of products of things raised to powers, things like this. And finding the derivative of this kind of expression would be pretty tricky. You'd have to have some big mix of quotient rules and chain rules and product rules. It'd be a real mess. But products and powers and quotients, those are all things that logarithms can simplify a lot. So there's kind of a nice trick that we can use with logarithms to make a derivative like this much easier to calculate. So what we're going to do is, if we start with an equation like this, y equals some function of x, what we'll do is take natural log on both sides. So we get natural log of y equals natural log of this big mess, x squared times the square root of 3 minus 2x all over e to the x times cosine of x. Okay, but now that we have this big mess of quotients and products inside of a logarithm, now we can start using properties of logarithms. So one property of logarithms is that the logarithm of a quotient is the difference of the logarithms. So natural log of x squared times square root 3 minus 2x minus natural log of the denominator, e to the x cosine x. But now we have these products inside of our logarithms, and products inside of a logarithm turn into sums outside the logarithms. So we get natural log x squared plus natural log 3 minus 2x. So square root of that, but I'm going to write that as a 1/2, a power of 1/2, minus, now we do have to be a little careful over here. We need a set of parentheses. But then we can use the same trick with turning the product inside into a sum outside. So natural log of e to the x, and then plus natural log cosine x. All right, well now we can go even further, because here we have some exponents inside of our logarithms, but another property of logarithms says that we can move those down in front. So this gives us 2 natural log x plus 1/2 natural log 3 minus 2x. And then over here, let's distribute this minus sign, I guess, here and here. But also, natural log of e to the x, that's just x. So minus x, minus, and then natural log cosine x. I don't think there's anything we can do to simplify that. Okay. Now at this point, we haven't calculated a derivative yet, right? All we have done so far is taken a natural log of both sides of this equation. So now let's take a derivative. But you can see that this thing on the right, taking its derivative is going to be a lot easier than taking the derivative of the thing we started with. So what we get here on the left, we do have to be a little careful to remember that we're taking a derivative with respect to x on both sides of this equation, right? So on the left, we have to use the chain rule. Derivative of natural log of y, well, that's 1 over the thing inside, which is y, times the derivative of y, which is dy dx. And then on the right-hand side, all of these derivatives are going to be pretty straightforward. So 2 times derivative of natural log x, that's 2 over x, plus 1/2 times derivative of natural log 3 minus 2x. So derivative of natural log is 1 over, and then put the inside in there, 3 minus 2x, and then multiply by the derivative of the inside. Well, the derivative of the inside here is just minus 2. So this 2 cancels that 1/2, minus derivative of x is 1, minus, and then here we have to be a little careful. So natural log, derivative of natural log is 1 over, and then put the inside in there, cosine x, and then multiply by the derivative of cosine, which is negative sine x. All right, and you can see all we have to do now is solve for dy dx. We are going to end up with a y on the right-hand side, but we know what y is. Y is right here. Right? So if we wrap all this stuff in parentheses, multiply both sides by y. Now we've solved by dy dx. We've solved for dy dx. All we need to do is express everything in terms of x. So this this y, let me write it up at the top because I've got another example waiting below. So now dy dx is y, which is x squared times the square root of 3 minus 2x over e to the x cosine x times all this stuff. So 2 over x minus 1 over 3 minus 2x minus 1, and then minus and minus means plus, and then sine over cosine, that's tangent. All right. So we did have to kind of set the stage by taking natural logs at the beginning and using the properties of logarithms, but I think it was worth it because it made the derivative part of this calculation much, much, much easier. This trick is called logarithmic differentiation. And it's a common trick to use when you are taking the derivative of something that's built out of exponents, quotients, and products. It doesn't work so well if you have lots of sums around, and that's because there is no logarithm law for having a sum inside or a difference. But if you have products, quotients, and powers, then logarithmic differentiation can make your derivative much easier to calculate. For one more example of this, let's calculate this derivative, the derivative of x to the sine x. Now, it's a little confusing how to start because on the one hand, we have the power rule, right? And the power rule says this, but the thing about the power rule is that n has to be a constant. The exponent has to be a constant. And that doesn't apply to this situation because sine of x isn't a constant. On the other hand, we have this derivative of an exponential, right? The derivative of a to the x is a to the x times natural log a. But for this logarithm law, the base, a, has to be a constant. And our base isn't a constant either. So these two derivative rules that we have figured out, we can't use either of them. So it seems like we're kind of stuck. Well, what we can do is do logarithmic differentiation. So name this function. So let's name it y. Y equals x to the sine x. Then take natural log on both sides. Natural log y equals natural log of x to the sine x. Now we haven't done any calculus yet. We're just setting the stage. All right, now we can use properties of logarithms. In particular, we can move this exponent down there. So we get natural log y equals sine x times natural log x. Now we can take a derivative with respect to x on both sides. So on the left-hand side, we have to do the chain rule because it's not x here, it's y. So derivative of natural log is 1 over, and then plug the inside into there, and multiply by the derivative of the inside, so that's dy dx. And then on the right-hand side, we have to do a product rule. So derivative of sine is cosine times the natural log with no derivative, plus sine with no derivative, times the natural log with a derivative, so that's 1 over x. And then we can multiply both sides by y, and we have our derivative. Dy dx is y, but right, going back to the original, y is x to the sine x times cosine x natural log x plus sine x over x. All right, so the upshot of this is, right, for a power rule, the exponent has to be a constant. For this exponential rule, the base has to be a constant. If neither of them are a constant, you can use logarithmic differentiation to handle that situation.